Think about how you experience the world. When you listen to a song, the sound sweeps smoothly through the air. When you look at a sunset, the colors blend perfectly into one another. We live in a fluid, continuous reality. In science, this smooth, uninterrupted flow is called analog. But the devices we use every day experience the world differently. Inside a computer's processor, there are no smooth transitions. There are only billions of microscopic switches, and a switch only has two possible states. It is either on or it is off. Because they only have two states, computers speak a language made entirely of two symbols, ones and zeros. This is called binary. Every piece of information must be broken down from a smooth reality into a rigid grid of ones and zeros. This raises a question. How can a machine built entirely out of simple on and off switches capture, process, and display the rich, colorful world around us? It has no eyes to see, no ears to hear, and no mouth to speak. Everything you see on a screen or hear through a speaker is an illusion. It is the result of a translation process that constantly forces our continuous reality into tiny, discrete digital boxes. Let's start with the easiest thing for a computer to translate: text. To turn letters and numbers into binary, computers use a system very similar to a secret decoder ring. This diagram shows exactly how that translation works. When you press keys on a keyboard, like a letter or a math equation, the input device generates a unique string of ones and zeros for every single character, sending that code directly to the computer. To ensure every computer translates codes exactly the same way, humans agreed upon a universal rulebook, the ASCII reference table. Looking closely at the lowercase t, the computer translates it directly into the binary value 1110100. Your phone or laptop matches patterns of ones and zeros against this dictionary thousands of times every second. Matching letters is relatively simple, but translating the complexity of a photograph, with all its varying shades and textures, requires a different approach. For most pictures, computers use a method called a bitmap. You can think of a bitmap as a digital mosaic. The computer chops the entire image into a massive grid of tiny squares, which we call pixels. It then looks at every single square and assigns a specific binary number to represent the exact color of that tiny piece. Because a single photograph might contain millions of pixels, saving the color code for every single square takes up a lot of storage space. Plus, if you zoom in too far, you start to see those jagged little squares. To fix this, for things like logos and fonts, computers use a second method called vector graphics. Instead of saving a giant grid of pixels, a vector graphic saves mathematical instructions. It tells the computer exactly how to draw the lines, curves, and shapes. No matter how far you zoom in, it recalculates the math and stays perfectly crisp. A computer's version of a picture is a massive color-by-number grid, or a set of strict mathematical instructions for drawing shapes. Sound presents an entirely different challenge. In the real world, audio is a continuous wave of pressure moving through the air. To capture that flowing wave, computers use a technique called a sampling rate. The computer takes rapid-fire snapshots of the sound wave's height. By measuring the wave thousands of times every single second, it builds a stepped digital approximation of the original sound. This creates a new problem: saving the color codes for millions of pixels and recording tens of thousands of audio samples every second results in files that are heavy and difficult to store. To fix this, the computer acts as the ultimate packer. It shrinks these files down for storage and internet transmission using a process called compression. There are two main ways to pack. Lossless compression finds clever ways to squish the data perfectly so absolutely no detail is lost. It is a lot like vacuum sealing your clothes in a plastic bag to fit them into a suitcase. When you open it back up, everything is exactly as you left it. But sometimes you need massive space savings. This diagram shows an MP3 file, which uses lossy compression. The computer chunks the audio into frames and throws away pieces of data that human ears are unlikely to notice, like frequencies too high to hear. To make the digital world fast and portable, devices are constantly calculating what sensory data is essential and what pieces they can safely throw away. We can see all of these concepts working together during a completely ordinary task: watching a streaming video on your smartphone. The moment you hit play, your phone downloads heavily compressed files from the internet and unpacks them in real time. Instantly, the processor translates millions of binary pixels to draw the image, simultaneously firing thousands of audio samples to create the sound. For the machine, this process is purely mathematical, flipping billions of microscopic switches on and off. But for us, sitting on the other side of the screen, we experience the emotion, the humor, and the tension of the scene. The computer handles the binary data, translating our analog world into the math required to create a flawless illusion for our senses. Thanks for watching.